In a stone farmhouse in the fields north of Oxford, a man in his 80s holds up a small triangle cut from cardboard, and he tells you that time does not exist. He has no university post. For 28 years, he paid for his life by translating Russian journals, buying himself a few quiet hours to think about the one question almost everyone assumes is already closed. What is time? His answer, worked out patiently over 50 years, is that the flow you feel right now is not a fact about the universe at all. There is no river carrying you forward. There are only frozen arrangements of everything there is, like frames on a strip of film, and the motion between them is something your own mind adds. And stranger still, when he looks inside Newton's 300-year-old theory of gravity, he finds the universe growing more ordered as it ages, not less. The exact opposite of what physics has taught for 170 years. So tonight, let's sit with a quiet, staggering possibility that the most obvious thing in the world, the passing of time, is the deepest illusion there is. Before we begin, if questioning reality, this slowly, is how you like to drift off, a quick like or subscribe genuinely helps the channel grow. It's a small thing for you, but it means a great deal to me. Now, let's begin. Part 1. The Man in the Farmhouse. Somewhere in the quiet fields north of Oxford, in an old stone farmhouse, there is a desk buried under papers, and on that desk, more often than you might expect, sits a small model made of cardboard. It is nothing more than a few flat triangles, cut by hand, the kind of thing a schoolchild might make on a rainy afternoon. The man who made it is in his 80s now. He has spent more than 50 years thinking about a single question, and for most of those years, almost no one was paying attention. He held no university post. He drew no salary from any physics department. He funded his life, and his family, and his thinking, by sitting at that same desk and translating scientific journals out of Russian, one page at a time, for 28 years. His name is Julian Barbour, and the question he has been turning over for half a century is one you have probably never thought to ask, because it seems too obvious to need asking. The question is this: what is time? You already know the answer, or you feel that you do. Time is the thing that passes. It is the ticking of a clock, the falling of the light through an afternoon, the slow accumulation of years on a face you love. Time is the river you are floating down right now, carried from the moment you began listening toward the moment you will drift off to sleep. It moves. It flows. It only ever goes one way. This is not a theory you hold. It is the water you swim in, so close and so constant that questioning it feels almost meaningless. Barbour questions it anyway, and the conclusion he has reached, patiently, carefully, from that farmhouse desk, is that the river does not exist. Time, he argues, is not a thing that flows. It is not a dimension we travel along. It is not the stage on which the events of the universe are performed. Time, he says, is an abstraction, something we deduce from change, in roughly the way we deduce a shadow from the object that casts it. There is no flowing. There is only the world, arranged one way and then arranged another, and the feeling of passage is something the mind lays over the top. I want to be careful and honest with you from the very beginning, because this is a channel that takes ideas seriously and does not oversell them. Julian Barbour has not proven that time does not exist. He would be the first person to tell you so, and later in this exploration, he tells us exactly that, in his own words. What he has done is something quieter and, in its way, more unsettling. He has taken an assumption so deep that most physicists never examine it, and he has shown that when you pull on the thread, an enormous amount of what we thought we understood about the universe begins, gently, to unravel. He has found strong hints inside the oldest physics we have, the physics of Isaac Newton, that the story we tell about time may be almost exactly backward. Before we go any further into the ideas, it is worth sitting for a moment with the strangeness of where they came from. We tend to imagine that the frontier of physics lives in enormous machines. We picture the tunnels of particle colliders, buried under the border of two countries, the mirrored tunnels of gravitational wave detectors, stretching for kilometers across the desert, the great telescopes perched on mountaintops in the thin, cold air. We imagine that if someone were going to overturn our understanding of time itself, they would do it there, surrounded by teams of hundreds and budgets of billions. Barbour did it in a farmhouse, alone, with cardboard triangles. He explains how, in a way that is almost disarming in its practicality. Years ago, someone told him that to make it in academia, he would need to publish 1 or 2 good research papers every year, reliably, forever. He knew, studying something as slow and as fundamental as the nature of time and motion, that he simply could not do that. The questions were too large and too patient to be sliced into annual portions. So he found another way to live. He could earn a reasonable amount of money translating Russian scientific journals into English, so he did that, for 28 years. And the translation work, demanding as it was, still left him roughly 1/4 to 1/3 of his time entirely free, free from the pressure to produce, free from the need to chase whatever the field happened to be excited about that season, free, simply, to think. He describes it without bitterness, almost with gratitude. He says it worked out very well. He had, over the decades, a series of remarkable collaborators, and slowly, steadily, for more than 50 years, he kept working away at these ideas, in his own time, at his own pace, answerable to no committee. There is a particular kind of freedom in that which the modern world has almost forgotten. Most of us are measured constantly by our output, by our visibility, by the metrics that scroll past on a screen. Barbour stepped outside of all of it, on purpose, and in doing so, he bought himself the one thing that a genuinely difficult question requires, which is time. There is an irony in that we will come back to, gently, at the very end. For now, I only want you to hold the picture in your mind as we begin. The fields north of Oxford, the cluttered desk, the little cardboard triangle held up to the light, and a man who decided, against all the incentives of his profession, to spend his one life asking whether the most obvious thing in the world is real. Because if he is right, then the flow you are feeling right now, the sense that this sentence comes after the last one and before the next, is not a fact about the universe at all. It is a story your mind is telling about a stack of frozen pictures. And to see why he thinks so, we have to start with the claim itself, laid out plainly, in all its quiet audacity. Part 2. The Heresy, stated plainly. Let me give you the heart of the idea now, without softening it, because the rest of everything we explore tonight grows out of this single seed. Barbour's claim is that there are instants, and that is all. He would say that an instant is a complete arrangement of the entire universe, every particle, every position, everything there is, captured all at once, like a single photograph of the whole of reality. Reality, in his picture, is an immense collection of these arrangements. He sometimes calls them nows, with a capital letter, to remind us that each one is a complete world, entire in itself. And what we call time, he says, is nothing more than a way of laying these nows in a sequence, one after another, and imagining that we move through them. Here is the crucial move, the one that takes a moment to feel. In Barbour's picture, the instants are real, but the duration between them is not. Think about that. The frozen pictures exist. The stretch of time you imagine connecting one to the next, the flowing interval, the passage, that is the thing he says we add. It is put in. It is not out there in the universe waiting to be measured. We deduce it, we insert it, we paint it across the gaps to make the still frames seem to move, in exactly the way a strip of film seems to move when you run it fast enough past a light. To make this concrete, Barbour reaches for his cardboard. Imagine, he says, that the entire universe consisted of just 3 particles. Not three particles floating in some larger empty space, but three particles and nothing else at all. No container, no backdrop, no stage. Those three particles sit at the corners of a triangle. That triangle, that particular arrangement of 3 points, is an instant. It is a complete ring. Now for that tiny universe. Change the arrangement. Move the particles so the triangle takes a different shape, and you have a different instant, a different now. The reality, Barbour insists, is just the triangles. The reality is the shapes. Time is the thing we imagine sliding between one triangle and the next to make it look as though they are evolving, as though one is causing the other, as though there is a current carrying us from this shape to that one. But there is no current, there is just this shape and that one. The universe does not pass from one to the next. The shapes simply are, all of them, and we, somehow, find ourselves reading them as a story. I know how this sounds on first hearing. It sounds like wordplay, like a philosopher rearranging definitions to sound profound. So let me anchor it to something you feel in your body, because the strangeness of the idea is real and worth sitting inside for a moment. Right now you have a powerful sense that this present moment is special. This now, the one you are in, feels lit up, alive, actual, in a way that yesterday afternoon does not, and in a way that tomorrow morning does not. The past feels gone, the future feels not yet real, and the present feels like a thin, bright edge, moving forward through the dark, the one place where things are actually happening. Barbour is telling you that the bright moving edge is a feeling, not a fact. Every now feels like the present when you are inside it. The you of yesterday afternoon felt exactly as vividly present as the you of right now. The you of tomorrow morning will feel exactly as present then. There is no single moving spotlight picking out one instant as the real one. Every instant contains its own conviction that it is the living present. And if that is so, then the flow, the passage, the sense of one special moment sweeping forward, is not something the universe is doing. It is something each frozen frame contains, sealed inside itself, like a photograph that somehow believes it is a film. There is an old line, one you may have heard before, that gets repeated in physics classes and in late-night conversations because it captures the intuition so neatly. Time, the line goes, is what stops everything from happening at once. It is a lovely phrase. It treats time almost as a kind of merciful spacing, a device that lays the events of the world out in an orderly queue so they do not all pile into a single unbearable instant. Hold on to that phrase. We are going to return to it at the very end, and when we do, Barbour will have turned it completely inside out. Because his suggestion, in the end, is that nothing stops everything from happening at once. In the deepest description, everything simply is. All the nows together, and the cue, the ordering, the one thing after another, is the mind's doing, not the world's. If you have ever made a flipbook as a child, you already hold the whole idea in your hands, and it is worth pausing on, because it makes the strangeness concrete. A flipbook is a stack of still drawings, each one slightly different from the last. A figure with its arm a little higher on each page. Nothing on any page moves. Each page is a frozen picture, complete and motionless. And yet when you riffle the pages past your thumb, you see a figure lifting its arm, smoothly, in motion, alive. Where is the motion? It is not on any page, because every page is still. The motion is not in the book at all. The motion is something that appears when a mind takes the still pictures in a certain order and fills in the gaps. The pages are real. The movement is added. Barbour is telling you that the universe is the stack of pages, and the flow of time is the riffling, and the riffling is done by you. Every now is a still page, complete and frozen, and the sense that they are streaming past, that one is becoming the next, is the mind doing what a mind does with any stack of nearly identical frozen frames, which is to see a flow that is not, in the pages themselves, actually there. The only difference is that in a flipbook, the pages sit in a definite order that you supply, and in Barbour's universe, the ordering itself comes from within the pages, from the shapes they contain, a subtlety we will come back to once we have built the tools to see it. Now, at this point, a reasonable person has every right to fold their arms. This is a strong claim, and strong claims deserve resistance. Why on earth should we take it seriously? Physics works, clocks tick, trains run on schedules. The equations of physics are full of a letter T for time, and they predict eclipses centuries in advance to the second. If time were an illusion, how could any of that possibly function? These are good objections, and Barbour has answers to them. Answers that took him 50 years to work out, and that reach back through 3 centuries of argument. But the first and most important thing to understand is that he did not invent this idea out of nothing. He inherited it. The suspicion that time is not fundamental is older than Einstein, older than the light bulb, older than the theory of the atom. It goes back to a quarrel between 2 of the greatest minds who ever lived, a quarrel about the nature of space and time that was never really settled, only set aside. And to understand why Barbour thinks the losing side of that quarrel was actually right, we have to go back 300 years, to Newton, and to the man who told him, to his face, that he was making the whole thing up. Part 3. The Quarrel Newton Won, and maybe shouldn't have. To feel the force of Barbour's idea, you have to understand what he is arguing against. And to understand that, you have to meet Isaac Newton's picture of the world at its most confident. Newton gave us, in the 1680s, a universe of breathtaking clarity, and I mean that in the plain sense, a clarity that let you breathe easily, because everything had its place. In Newton's cosmos, there is absolute space, a real, fixed, infinite arena that exists whether or not anything is in it. And there is absolute time, a real, uniform flow, the same everywhere, that would go on ticking even if the entire universe were empty and nothing ever changed. Space is the stage, time is the clock hanging above the stage. And on this stage, against this clock, matter moves according to Newton's laws, in straight lines unless something pushes it, tracing out its motions in a container that was there before it and would remain after it was gone. Barbour has a wonderful image for what Newton was really proposing. Imagine, he says, that absolute space is like an enormous block of transparent ice, infinite in every direction, perfectly clear, completely invisible. In that block of ice you could, in principle, score straight lines, mark out true directions, define what it means to move without turning. That is what Newton's absolute space does. It is an invisible scaffolding of true positions and true motions, present everywhere, needing nothing to hold it up, the silent grid against which everything else is measured. It is a powerful picture. It is also, Newton's great rival insisted, complete nonsense. That rival was Gottfried Wilhelm Leibniz, a German philosopher and mathematician who, among other things, invented the calculus at roughly the same time Newton did, which tells you something about the caliber of mind we are dealing with. Leibniz looked at Newton's block of invisible ice and asked a devastatingly simple question. How would you ever score a line into it? If you take a real block of ice, you can drag a blade across it and leave a mark, because the ice is made of something. But Newton's space is made of nothing. It is invisible, intangible, featureless. You could never actually mark a position in it, never actually point to a place and say the motion started here and ended there, because there is nothing there to point at. The straight lines Newton imagined were, Leibniz said, lines drawn on emptiness. They referred to nothing real. So Leibniz offered a different picture, and it is the picture Barbour has spent his life developing. Space, Leibniz said, is not a thing. Space is a relationship. Space is, in his exact phrase, the order of coexisting things. When people pressed him on what he meant by order, he answered with beautiful directness. He meant the distances between things. Space is nothing but the fact that this object is a certain distance from that one, and that one a certain distance from a third. Remove all the objects and you do not have empty space left over. You have nothing at all, because space was never a container. It was only ever the web of relationships among the things it seemed to contain. And time, Leibniz said, is the same kind of thing. Time is not a river flowing behind the events. Time is the order of succession among things. It is the fact that this arrangement is followed by that arrangement. Take away the changing arrangements, and you do not have empty time ticking on in the dark. You have nothing, because time was never a separate flow. It was only ever our name for the fact that the world is arranged differently from one configuration to the next. Now, to be fair to Newton, and this channel always tries to be fair to the losing and the winning side alike, Newton had a powerful reply, and it is worth meeting, because Barbour has to answer it. Newton pointed to rotation. Take a bucket of water, he said, and hang it from a twisted rope, and let it spin. At first the bucket turns, but the water sits still and flat. Then, gradually, the water begins to turn with the bucket, and as it does, its surface climbs up the sides and hollows into a curve. Now, Newton asked, what is the water responding to when it curves? Not to its motion relative to the bucket, because the surface is most curved exactly when the water and the bucket are turning together, at rest relative to each other. The water seems to know that it is really rotating, absolutely, regardless of anything nearby. And what could it be rotating relative to, if not absolute space itself? The curving water, Newton argued, is direct evidence that absolute space is real, that there is a true difference between spinning and not spinning that owes nothing to the other objects in the world. It is a genuinely formidable argument, and for 2 centuries it was considered close to decisive. Mach's great contribution was to answer it. The water, Mach said, is not rotating relative to absolute space. It is rotating relative to all the matter in the universe, relative to the distant stars, relative to everything there is. The bucket experiment has been performed, in effect, with the entire cosmos looking on, and it is the cosmos that provides the standard of non-rotation. To really test Newton's claim, Mach pointed out, you would have to spin the water in a truly empty universe, with no stars, no distant matter, nothing, and see whether the surface still curved. Nobody can perform that experiment, so Newton's confident reading of the bucket is not forced on us. The water may be responding not to invisible absolute space, but to the visible weight of all the matter in the sky. This is Mach's principle again, in its most vivid form, and it is exactly the thread Barbour picked up and never let go. Newton won this argument, in the practical sense that matters most. His physics worked, spectacularly, and Leibniz's objections, however philosophically sharp, did not come with a better set of equations. So the world took Newton's absolute space and time and built 3 centuries of triumphant science on top of them, and Leibniz's protest faded into a footnote for philosophers. But it did not die. A century and a half later, it came roaring back, in the work of an Austrian physicist named Ernst Mach. Mach, in the 1870s, said essentially what Leibniz had said, but he said it as a physicist, with a physicist's precision, and he added a sting that would prove enormously important. Mach's line about time is one Barbour quotes, almost like a mantra, and I want you to hear it slowly, because it is the philosophical seed from which everything else grows. It is utterly impossible, Mach wrote, to measure the changes of things by time. Quite the contrary. Time is an abstraction at which we arrive through the changes of things. Listen to what that reverses. We think we measure change by time. We think time is the fundamental yardstick, and change is what we lay against it. The clock is real, and the moving thing is measured against the clock. Mach says no, you have it exactly upside down. There is no clock hanging in the sky. There is only change, only the world rearranging itself, and time is the abstraction we squeeze out of that change, after the fact. a summary we invent to describe how things vary relative to one another. The clock does not measure the motion. The motion is all there is, and the clock is just one more moving thing we have agreed to compare the others to. Mark went further, into the question of motion itself, and here he planted the seed that would eventually flower into Barbour's whole program. What does it mean, Mark asked, to move in a straight line, to move without turning, to be in what physicists call an inertial frame? Newton would say it means moving in a straight line through absolute space. But there is no absolute space to move through. So what actually fixes the difference between spinning and not spinning, between turning and going straight? Mark's answer was radical. It is fixed, he said, by all the matter in the universe. The local standard of straight-line motion, right here, is determined by the relative positions and motions of everything out there, every star, every distant scrap of matter in the entire cosmos. Physics, for Mark, was not something that happens to isolated objects in an empty box. It was holistic. To describe the motion of a single thing correctly, you had, in principle, to take into account the whole universe. This idea that the local is secretly determined by the global, that what happens here is quietly shaped by everything out there, became known as Mark's principle. It was a great stimulus to the young Albert Einstein and helped push him toward general relativity. But Barbour argues, and this is a lovely and slightly mischievous part of his story, that Einstein did not really follow Mach through to the end. Einstein took some of the inspiration and then, with the help of wonderful mathematics, built a theory that in some ways muddled what Mach had actually been saying. Much of Barbour's long life has been spent, in his own words, trying to sort out that muddle, to recover the clean relational insight that he thinks got tangled up along the way. He tells a story about this that is worth pausing on, because it says something about the whole culture of physics. Barbour once found himself in conversation with a distinguished astrophysicist, a serious and accomplished scientist, who began confidently explaining to him what Mach's principle really was, what Mach had really meant, what Mach had really required. And Barbour, who has read Mach's actual books with enormous care, listened, and then said, as gently as he could, that what the man had just described was his interpretation of one famous physicist's interpretation of Einstein's interpretation of Mach. It was Mach at fourth hand, filtered through a chain of authorities, none of whom, it turned out, had gone back to the source. And the astrophysicist, to his credit, admitted it at once. He said, "You are quite right. I have never read a word of Mach." There is something both funny and a little sad in that exchange, and it captures the strange position Barbour occupies. Here is a man sitting in a farmhouse in the countryside, reading the original works, thinking from the ground up, largely ignored, because the assumption in the field is that Einstein must simply be right, and there is nothing left to re-examine. And here is the establishment, brilliant and busy, confidently repeating a version of an idea that has been passed down so many times that no one remembers to check it against what its author actually wrote. Barbour is not angry about this. He seems, if anything, amused by it. But it tells you why his ideas took 50 years to develop in near silence. He was not building on the consensus. He was going back underneath it, to the quarrel between Newton and Leibniz that everyone else considered long since closed, and asking whether the side that lost had actually been right all along. And to show you that the losing side might be right, Barbour does not appeal to grand philosophy or to sweeping cosmic claims. He does something far more clever and far more humble. He picks up his cardboard and he builds you the smallest possible universe, and he asks you to look at it very, very carefully. Part 4. The smallest possible universe. To follow Barbour into the deepest part of his idea, you have to be willing to do something that sounds almost childish. You have to be willing to imagine a universe made of just a few points, and to take that toy universe completely seriously, as if it were everything there is. Barbour does this constantly, and there is a reason. He believes that the confusions we have about space and time come precisely from imagining that things sit inside a container. If you build a universe small enough, you can see, with total clarity, that there is no container, and that everything you thought was a property of the space is really a relationship between the things. So let us build it with him, slowly. Let us start with the very smallest universe we can, and work our way up, and let the strangeness arrive one careful step at a time. Settle in for this. There is nothing to memorize here, and nothing to strain toward. There is only a series of small pictures, each one a little stranger than the last. Begin with a universe containing exactly one particle, one point, and nothing else. No space around it. Because space, remember, is only the relationships between things, and there is only one thing, so there are no relationships, and so there is no space. Now ask yourself a simple question: where is the particle? And you find, if you are honest, that the question has no meaning. There is nowhere for it to be, because there is no elsewhere to compare it to. There is no left or right, no near or far, no here as opposed to there, because all of those require at least two things. A one-particle universe is, as Barbour says, a universe in which nothing whatever can be said. It would see nothing, know nothing, contain nothing but a single mute point about which no question has an answer. It is not interesting. It is barely a universe at all. So add a second particle. Now there are 2 points, and immediately something appears that did not exist before. There is a separation between them. There is a distance, the one and only fact this universe contains. But notice how thin that fact is. You can say the 2 particles are apart, or you can say they are on top of each other, and that is nearly the whole story. And there is a subtlety Barbour is careful about. Without a ruler sitting outside the universe, you cannot even say how far apart they are, because a distance only becomes a number when you compare it to some other length. In a universe with only 2 particles and nothing else, there is no other length to compare it to. There is just the bare fact of separation, a relationship with no size. It is more than the one-particle universe had, but only barely. 2 particles still cannot make anything you could call a world. And then you add the 3rd particle, and everything changes. I want you to feel this, because it is the moment Barbour builds his entire cosmos on, and it arrives with a kind of quiet click. With 3 particles, for the first time, you have a shape. 3 points define a triangle, and a triangle is not just a collection of distances. It is a form. It has angles. It has proportions. It can be squat or pointed, balanced or lopsided, and here is the beautiful thing. You can describe the shape of that triangle completely, without any ruler at all, without any external space, without anything outside the 3 particles themselves. The triangle carries its own form, intrinsically, in the relationships among its 3 points. A whole world of qualities, of distinctions, of this shape versus that shape, springs into being the instant you have 3 things instead of 2. This is why Barbour says, the first genuine universe, the first one where anything interesting can happen, has 3 particles. And it is why he illustrates everything, patiently, endlessly, with triangles. A triangle is the simplest thing in existence that has a shape. Below 3 particles, there is only distance, or not even that. At 3 particles, form is born. Now hold that triangle in your mind, and let me hand you Barbour's picture of time, built entirely out of it. Imagine that our 3-particle universe is arranged, right now, as one particular triangle, tall and narrow, let us say, with 2 points close together and 1 far off. That triangle is an instant. It is a complete now for this universe. Everything there is, captured whole. Now imagine another triangle, a different shape, wide and flat this time. That is another instant, another now. And a third, nearly equilateral, all 3 points evenly spread, another now. Here is the question that unlocks everything. What connects these triangles? What carries the universe from the tall, narrow one to the wide, flat one to the balanced one? Your instinct screams that there must be something, a flow, a passage, a stream of time, along which the triangle changes its shape, the way a movie changes from frame to frame. But look at the triangles themselves. Look at just the three shapes, laid out. Is the flow in them? Is the passage anywhere in the actual arrangements of the 3 points? It is not. There are only the shapes, the tall one, the wide one, the balanced one. Each is complete. Each is just a fact about 3 distances. The stream you imagine running between them, carrying one into the next, is nowhere to be found in the triangles. It is something you are supplying, from your own habit of mind, painting motion across a set of still pictures. The reality, Barbour says, is just the triangles. The reality is the shapes. Time is what you put in between them so that they seem to move. Let yourself go there now. You are inside a universe with 3 points of light and nothing else. There is no floor beneath them and no sky behind them. Because there is no space at all, only the 3 lights and the distances between them. One arrangement holds. 2 lights near, 1 far. A tall, thin triangle, hanging in a darkness that is not even darkness. Because darkness would be something, and there is nothing here but the 3. And now another arrangement. The far light has swung close. The near ones drifted apart. A wide, flat triangle. But notice, as you hover here, that nothing moved. You did not see the first triangle slide into the second. There was this shape, and there is that shape. Between them there is no journey, no travel, no smooth transformation, because there is no time in which any travelling could happen. There is only one complete world, and another complete world, and your mind, reaching helplessly for a story, insisting that one must have become the other. But they simply are. Both of them, all of them, every triangle this universe can hold, existing not one after another, but simply existing, and you, somehow, moving among them in a way that is starting to seem less and less like motion at all. Come back now, gently. Open your attention to the room again. Because if you felt even a flicker of that vertigo, the strange loosening of the certainty that one moment leads to the next, then you have felt the thing Barbour has been trying to show people for 50 years. And notice what did the work. It was not a lecture about the philosophy of time. It was 3 dots and the shapes they can make. That is the method. Build the universe small enough to see it whole, and the container you thought was holding everything up simply vanishes, and you are left with nothing but shapes and the relationships inside them. But we have smuggled something in without examining it, and Barbour is far too careful to let it pass. When I described those triangles as tall or wide or balanced, I was quietly assuming you could tell how big they were. I said 2 points were close, and 1 was far. Close compared to what? Far measured how? I was sneaking a ruler into a universe that, by construction, has nothing outside it to measure with. And when Barbour pulls on that thread, when he asks what size even means for a universe that contains everything, the floor tilts again, further than before, because it turns out that the size of the universe, the very bigness of things, may be as much of an illusion as the flow of time, and that is where we turn next. Part 5. The ruler that was never there. We have to talk about size, because size is where our intuitions put up their most stubborn fight, and where Barbour lands one of his most beautiful blows. You feel, absolutely certainly, that things have a size. This room has a size. Your body has a size. The Earth is a certain size, and the Sun is much bigger, and the galaxy is unimaginably bigger still, and all of these are simple facts, as solid as anything you know. Size seems like the most basic property a thing can have, more basic even than shape, because before something can have a form, it surely has to have an extent, a bigness, a measure of how much of the world it takes up. Barbour asks you to question even this, and he does it with a thought experiment borrowed from one of the greatest mathematicians who ever lived, the Frenchman Henri Poincaré. In a book called Science and Method, written in the first decade of the 20th century, Poincaré posed a strange scenario. Suppose that in one night, while you slept, every single dimension in the universe became 1,000 times larger. Everything, not just you, but your bed, your house, the earth, the distance to the sun, the size of every atom in your body, the wavelength of every ray of light, all of it, multiplied by 1,000, uniformly, in perfect proportion. What was a meter is now a kilometer. What was a millimeter is now a meter. You, and everything you could ever use to measure yourself, have all grown together in exactly the same ratio. Now, Poincaré asks, when you wake in the morning, what will you notice? What will be different? And the answer, when you think it through, is nothing. You will notice nothing at all. You cannot measure your new size, because your ruler grew too. You cannot tell that the room is larger, because your body grew in step with it. Every possible comparison you could make has shifted by the same factor, and so every comparison comes out exactly as it did before. The thousandfold expansion is completely undetectable, from the inside, forever. And Poincaré draws the sharp conclusion. The change, he says, only exists for someone who imagines that space is absolute, that there is some external ruler, some godlike measuring stick outside the universe, against which the true size could be read. For anyone inside, there is no such ruler, and so there is no such fact. The absolute size of the universe is not a real quantity at all. Here is what fascinates Barbour, and what he says, almost with a kind of affectionate frustration. Poincaré saw this perfectly. He understood, 120 years ago, that absolute size is meaningless, that only the proportions, only the shapes, are real. And then he did nothing with it. He noticed the loose thread, and did not pull. He never produced a quantity, a piece of mathematics, that would capture the shape of things while ignoring their size, that would change when the proportions changed, and stay silent when the whole universe merely scaled up or down. That missing quantity is exactly what Barbour would spend his life building, and it is the thing we will meet in the next part. But first I want you to sit with the disorientation, because it is worth feeling fully. Think again about our triangle. When I said it was tall and narrow, or wide and flat, those were statements about its shape, its proportions, and those are real, intrinsic, needing no ruler. But if I had said the triangle was 10 centimeters across, I would have been lying, or rather, I would have been referring to a ruler that does not exist. In a universe that is only 3 particles, there is no centimeter, no meter, no unit of any kind, because a unit is just another length you have agreed to compare things to, and there are no other lengths. The triangle has a shape, it does not have a size. Its size is not small, and it is not large. Its size is simply not a question the universe can answer. Barbour has a lovely way of making this vivid. Imagine, he says, that the triangle could feel itself, the way you can feel where your own limbs are without looking. You know right now, roughly, how far your 2 hands are apart, not because you are measuring them against anything external, but through a direct inner sense, the sense that lets you clap without watching your hands. Now suppose the triangle had that inner sense. What would it feel? It would not feel its size, because size requires an outside ruler, and the triangle has no outside. What it would feel is its angles. Each corner would sense the directions to the other 2 corners, the angle spread between them, and from those angles alone, the triangle would know its own shape completely, because the 3 angles of a triangle always add to 180 degrees, and the shape is fixed once you know how that 180 is divided among the corners. So the triangle, feeling itself from the inside, knows its shape and knows nothing of its size, and this, Barbour suggests, is exactly the right way to think about our own universe. When cosmologists speak of the universe expanding, Most of us picture it swelling against some external backdrop, growing into a surrounding emptiness, getting bigger, in the way a balloon gets bigger in a room. Barbour is deeply skeptical of that picture. He suspects the cosmologists have quietly imagined a ruler outside the universe, a cosmic measuring tape against which the expansion is read, and that no such ruler exists. What is actually changing, he would say, is not the size of the universe against some outside standard, because there is no outside standard. What is changing is the shape, the internal proportions, the relationships among all the things the universe contains. Expansion, properly understood, is not the universe getting bigger, it is the universe changing shape. Let me try to give you a feeling for how that can be, because it is genuinely counterintuitive, and Barbour has a small demonstration that helps. Take a triangle, and imagine it is the whole universe. Ask, which triangle is the smallest? You might think you cannot answer without a ruler, but there is a way. Among all the triangles with the same corners, the most balanced one, the equilateral triangle where all three sides are equal, is in a certain intrinsic sense the most compact, the most gathered in. Now let the triangle become more pointed, more stretched, two corners pulling apart, while the third stays close. Measured against its own shortest side, the triangle is getting longer and longer, more and more drawn out. From the inside, using only its own proportions, the triangle would say, it is getting bigger. It is expanding, and yet nothing has been measured against any external ruler at all. The expansion is purely a change in the internal shape, in how the corners are arranged relative to one another. That, Barbour proposes, is what the expansion of the universe really is. Not growth against a backdrop, but a change in the cosmic shape, felt from within as a spreading, a stretching, an increase, with no outside ruler anywhere in the story. Do you feel how much has quietly been stripped away now? We began by doubting the flow of time. Now we are doubting the size of things. Two of the most basic seeming features of reality, how big the universe is and how fast time is passing, have both dissolved into something else, into relationships, into shape, and notice that they are dissolving in the same direction. In both cases, the thing we imagined was fundamental, the flowing time and the absolute size, turns out to require an external reference that is not there. There is no clock hanging outside the universe by which to measure its ticking. There is no ruler standing outside the universe by which to measure its size. In each case, when you remove the imaginary external standard, what remains is not emptiness. What remains is the shape, the pattern, the web of relationships, and Barbour's whole claim is that this remaining thing is not a poor substitute for reality. It is reality. It is the only thing that was ever actually there. It is worth dwelling on why the standard picture of cosmic expansion bothers Barbour so much. Because his objection is subtle, and it sharpens the whole idea. When you have seen the expanding universe explained, you have almost certainly seen the balloon. Dots are drawn on the surface of a balloon, and the balloon is inflated, and the dots move apart, and you are told that this is how galaxies recede from one another as space itself stretches. Or you have seen a sheet of elastic with buttons pinned to it, stretched wider and wider, the buttons drifting apart. These are useful pictures, and I have used them myself. But notice what they quietly smuggle in. The balloon expands into the room around it. The elastic stretches against the ruler of the table beneath it. In every one of these images, the expanding thing is embedded in a larger space, a background, an external frame against which the growth is measured. And Barbour's whole point is that the universe has no such background. There is no room around the balloon of the cosmos. There is no table beneath the cosmic elastic. When cosmologists speak of space itself expanding, Barbour suspects they are still, without quite noticing, picturing an external ruler, a godlike measuring tape laid alongside the universe, and then imagining the universe growing against it. Remove the ruler, as honesty demands, and the word expansion has to mean something else entirely. It cannot mean the universe getting bigger, because bigger requires the ruler that is not there. It can only mean the universe changing shape. He is careful to say he is skeptical, not certain, about how the professionals handle this. He does not claim to have overthrown modern cosmology in an afternoon. He says, plainly, that he has not worked through every detail of how the standard models treat scale, and that these are difficult matters. But the suspicion is precise, and it is serious. If size is not a real quantity, if only shape is real, then a great deal of what we say about the universe, its size, its age, measured against some absolute clock, its expansion into some surrounding frame, may be built on a foundation that quietly assumes the very external ruler that Poincaré showed cannot exist. And that suspicion is not idle philosophy. It has teeth, because it points directly at the number Barbour did manage to write down, the number that captures shape while ignoring size, and lets you do real physics without ever pretending there is a ruler outside the world. Which brings us to the quantity Poincaré never wrote down. If size is meaningless and only shape is real, then to do physics, to say anything precise about the universe, you need a number that captures shape, and shape alone. A number that would not budge if the whole cosmos grew 1,000-fold overnight, but that would change, sensitively and meaningfully, whenever the proportions of things actually shifted. Barbour found that number, and when he found it, he discovered something that stopped him cold, something that turned a philosophical curiosity into a claim about the fate of the universe. Because the number that measures the pure shape of things, it turned out, had been hiding, in plain sight, for 300 years, inside Isaac Newton's theory of gravity. Part 6. The number that measures order. I am going to describe to you the most important quantity in Julian Barbour's work, and I am going to do it without a single equation on the screen, because you do not need the symbols to feel what it does. You only need to follow a simple recipe, one step at a time, and then to notice the astonishing thing that happens at the end. Barbour calls this quantity the complexity. Other physicists, the specialists who study how large groups of bodies move under gravity, call it the shape potential, or the normalized Newton potential. The different names are all pointing at the same number, and the number does one job. It measures how structured, how clustered, how varied an arrangement of matter is, using nothing but the shape, with the size stripped away. Here is how you build it. Imagine a universe of particles, as many as you like, scattered through space. First, take every pair of particles and note the distance between them. If there are many particles, there will be many such distances, one for each pair. Now, from all these separations, you are going to build two different numbers and then combine them. The first number captures the overall size of the whole arrangement. You take all the separations, square each one, add them up, and take the square root of the total. This gives you a kind of average length, a single number standing in for how spread out the whole collection is. Physicists call it the root mean square length, but you can just think of it as the size number. When the particles are spread far apart, this number is large. When they are packed close together, it is small. It is, in effect, the ruler, the overall scale of the system. The second number captures something quite different. This time, you take each separation and form 1 divided by that separation, and you add all of those up. This is the closeness number, and it behaves in an interesting way. When two particles are far apart, 1 divided by their large separation is a small contribution. But when two particles come close together, 1 divided by their tiny separation becomes enormous. And if two particles were ever to touch, 1 divided by 0 would blow up to infinity. So the closeness number is exquisitely sensitive to particles clumping together. It barely notices particles that are spread out, and it screams whenever particles gather. Now, here is the recipe's final step. You multiply the two numbers together, the size number and the closeness number. And when you do, something almost magical happens. The The size number grows when you scale the whole system up, and the closeness number shrinks by exactly the same factor when you scale the whole system up, because a larger system has larger separations, which make 1/over separations smaller. The two effects cancel perfectly. The product does not care about the overall size at all. Blow the whole universe up 1,000-fold, as in Poincaré's dream, and this number does not move. It is scale invariant. It is ruler invariant. It is a pure number that depends only on the shape. This is the quantity Poincaré never wrote down. Barbour wrote it down, and it does exactly what shape requires. If the particles are spread out smoothly and evenly, with nothing clustered, the complexity is low. If the particles are gathered into clumps, into groups within groups, into structure and pattern and hierarchy, the complexity is high. The number rises as the arrangement becomes more intricate, more organized, more full of distinct parts. It is, as nearly as anything can be, a measure of order, a measure of how much interesting structure a universe contains. Barbour did not arrive at this number by cold calculation. He arrived at it by chasing an idea he had fallen in love with, decades earlier, reading the philosophy of Leibniz. Leibniz had this haunting notion that the fundamental drive of reality is toward variety. Without variety, Leibniz wrote, there would be nothing. We could see nothing, say nothing, distinguish nothing, because everything would be the same featureless sameness. The whole of our existence, all of it, rests on the fact that things differ, that there is this as opposed to that. And Leibniz went further, in his grandest and strangest work, and proposed that the actual universe, the one we live in, is the one that achieves more variety than any other possible universe, while running on the simplest possible rules. Maximum richness, minimum law. That, for Leibniz, was the signature of reality. Barbour was gripped by this, and spent years trying to turn it into mathematics, trying to find the number that would measure Leibniz's variety, that would grow as the universe became more varied. He was not alone in the attempt. He introduced Leibniz's ideas to the physicist Lee Smolin, and Smolin wrote one version, and Barbour wrote another, and for a while, neither was quite satisfying. And then, around the year 2011, working with specialists in Newton's theory of gravity, Barbour realized that the quantity he was looking for was one these physicists already knew well, under a different name. The measure of Leibniz's variety, the number that captures the pure shape of a clustered universe, was, apart from a minus sign, exactly the Newtonian gravitational potential, the very thing from which the familiar 1/distance squared force of gravity is derived. Sit with that for a moment, because it is the kind of coincidence that makes physicists go very quiet. Leibniz, in the 1690s, dreaming philosophically about a universe striving toward maximum variety. Newton, his bitter rival, in the same decade, writing down the mathematics of gravity, the force that pulls the planets and drops the apple. Two men who could barely stand each other, working on what seemed like utterly different things, one on metaphysics and the other on falling bodies. And 300 years later, it turns out that Leibniz's dreamed-of measure of cosmic variety and Newton's hard-headed formula for gravity are, up to a sign, the very same number. The quantity that measures how much structure and order a universe holds was sitting inside the theory of gravity the entire time, and nobody had thought to read it that way. Let me give you a feeling for how this number behaves, because a feeling is worth more here than any formula. Picture a few thousand particles scattered as evenly as possible through a region, like a fine, even mist. No clumps, no gaps, every particle roughly the same distance from its neighbors. In that smooth arrangement, the closeness number stays modest, because no two particles are jammed unusually close, and so the complexity, the product of size and closeness, sits low. Now let the arrangement change. Let some particles drift together into a knot over here, and others gather into a clump over there. and let those clumps arrange themselves into larger groupings, clusters of clusters. Every time two particles come close, the closeness number jumps, because 1 divided by a small separation is large. The mist has become a structure, a hierarchy, a thing with parts and subparts and distinct regions, and the complexity has climbed to match. That is all the number is doing. It is listening for clustering, for the gathering of matter into distinct forms, and reporting how much of it there is. Low complexity means smooth and featureless. High complexity means structured and various. It is, in the most literal sense the mathematics allows, a meter for order. And the reason Barbour trusts it, rather than any of the 100 other numbers one might cook up, is that it is very nearly the simplest thing that does the job. He follows a rule he attributes to Einstein, one he says he actually approves of, which is that when you have a genuinely new idea, you should try it out first on the simplest non-trivial case, and not dress it up in complications you do not yet need. The complexity is about as simple as a shape measure can be. You could build more elaborate versions, and Barbour acknowledges there are many possible variations, but the essential behavior, the scale invariance, the sensitivity to clustering, survives in all of them, because it flows from the one principle he insists on, which is that only shape is real and size is not. So he takes the simplest version and follows it, and it leads him somewhere no one expected. This is the moment Barbour's project stopped being philosophy and became physics with teeth. Because if the complexity, this measure of order, is built right into Newton's gravity, then you can ask a hard, precise mathematical question. As a gravitating universe evolves, as its particles move under their mutual attraction, what does the complexity do? Does it rise or fall? Does the order of such a universe increase over time or decrease? And the answer Barbour found, working through the mathematics of Newton's own theory, is the answer that put him on a collision course with one of the most sacred laws in all of science. Because the complexity, in these universes, tends to increase, the order grows. And that is very nearly the opposite of what we have been told for 170 years that the universe must do. Part 7. The most uniform moment. Before we reach the collision, we have to understand one more thing, the strangest and most beautiful result in this whole story, because it is the hinge on which everything turns. We have to understand what the most orderly and simultaneously the most uniform arrangement of a gravitating universe looks like, and where it sits in the history of such a universe. Start with the complexity, that number we just built, the measure of shape and structure. Because it is made by multiplying and adding quantities that are always positive, the complexity itself can never be negative. It has a flaw, and a quantity with a flaw must have a lowest possible value, an absolute minimum, a shape at which it bottoms out. Barbour has studied this minimum with great care, and he gives it a name. He calls it alpha, the first letter, the beginning, and alpha has a property that is worth savouring slowly. The shape of alpha, the arrangement that minimizes the complexity, is the most uniform arrangement possible. It is the smoothest, most even, most balanced distribution the particles can take. There is an image Barbour likes to show, made available to him by an astronomer in Manchester named Richard Batty, and reproduced in Barbour's book. It shows roughly 5,000 particles arranged in this special minimal shape. On one side, you see them as a three-dimensional ball, and on the other side, you see a slice through the middle, an equatorial cross-section. And what strikes everyone who sees it is how smooth it is. Not perfectly, mechanically uniform, like dots on a grid, but smooth in the natural way that a still pond is smooth, or a fine mist, evenly filled, with no great gaps and no great clumps, particles spread through the ball as gently and regularly as the mathematics will allow. Now here is the first surprise. You might think that the most uniform arrangement, this smooth, even ball, is the most boring, the least structured, the arrangement with the least going on, and in a sense it is. But it is held in that smoothness by a delicate and dynamic balance, and the balance is guaranteed by a theorem that Newton himself proved. Newton showed that outside a spherically symmetric ball of matter, gravity behaves exactly as if all the mass were concentrated at the single point in the center. This is why we can treat the Earth, for many purposes, as though all its mass sits at its core. Barbour uses this theorem to explain why the smoothest arrangement is a genuine equilibrium, a shape that gravity itself sustains. Every particle feels a pull toward the common center, growing stronger with distance, and the whole thing is held in a poised, balanced state that mathematicians call a central configuration or a relative equilibrium. He points out with characteristic precision that this perfect uniformity only works in 3 dimensions, and only for the particular way gravity falls off with distance in our universe. Change the number of dimensions, or change the law of the force, and the beautiful smoothness fails. Our universe seems to be built with exactly the right rules for it to work. And now the second surprise, the one that gives me a genuine chill every time I think about it. To find it, we go back to the year 1907, to a Finnish mathematician named Carl Sundman. Sundman was studying the oldest hard problem in physics, the question of how several bodies move under their mutual gravity, and he asked a very particular question. Is it possible, under Newton's laws, for a group of particles to fall together and collide all at once, every one of them arriving at the common center at the very same instant? A total collision, the whole system crashing into a single point together. Sundman proved that yes, it is possible, but only under strict and specific conditions. The system must have no overall rotation, no spin. The total angular momentum must be exactly 0, and as the particles rush toward their shared doom, their shape must become very special, settling into either a perfect equilateral triangle in the 3-body case, or a precise straight line. A year later, in 1908, a mathematician named Bloch extended the result, showing that essentially the same thing holds for any number of particles, not just 3. So we have this picture, from the early 1900s, of many particles falling inward, growing more and more uniform and symmetric as they approach a single catastrophic instant of total collision. And now Barbour does the one thing that unlocks the universe. He remembers that Newton's equations do not care about the direction of time. They work equally well run forward or backward. Every solution played forward is also a valid solution played backward. So take Sundman's total collision, that swarm of particles crashing together into a smooth, symmetric point, and simply run the film in reverse. What do you see? You see a smooth, symmetric, extraordinarily uniform state, and then you see it explode outward. You see everything begin at maximum evenness and fly apart, expanding, the particles streaming away from that special uniform beginning. You see, in other words, a Big Bang. A Newtonian Big Bang, an explosion outward from a state of near-perfect uniformity, falling straight out of Newton's 300-year-old theory of gravity, requiring no exotic new physics, no quantum fields, no cosmic inflation, just particles, and gravity, and the reversal of a collision. And Barbour is quick to point out the astonishing timing of this. Sundman proved his result in 1907. Bloch generalized it in 1908. Edwin Hubble did not publish his discovery that the real universe is expanding until 1929, more than 20 years later. The mathematical seed of an expanding universe, beginning from a uniform state, was sitting in the theory of gravity 2 decades before anyone looked through a telescope and saw the galaxies actually flying apart. There is a further consequence here that Barbour finds tantalizing, and it touches one of the proudest achievements of modern cosmology. Cosmologists have long treasured something they call the cosmological principle, the idea that if you look at a large enough region of the universe, it looks essentially the same as any other equally large region, anywhere else. The universe, on the grandest scale, is smooth and uniform, the same in every direction and every place. Explaining why the universe should be so evenly filled is a serious problem, and the standard answer invokes cosmic inflation, a burst of enormous expansion in the first fraction of a second that is supposed to have smoothed everything out. But look again at Barbour's uniform beginning, that smooth, even ball of the alpha shape. If you were to drop a small coin anywhere onto a slice of it, the patch it covers would look much like the patch it would cover anywhere else. The arrangement satisfies the cosmological principle automatically, by its very nature, as a consequence of Newton's theorem and the structure of the complexity. And so Barbour raises the possibility, cautiously, that the smoothness of the universe might not require inflation at all, that it might follow directly from the same old 300-year-old gravity and the same shape measure we have been building, the uniformity coming for free rather than being manufactured by an exotic early universe event. He does not insist on it, but he notes with evident pleasure how much falls out of so little, how a smooth, expanding universe, satisfying the cosmological principle, drops straight out of Newton, complexity, and the reversal of a collision, with nothing exotic added. So come and stand at the beginning of one of these universes, let everything else fall away, and let there be only a ball of countless points of light, smoother than seems possible, hanging in a stillness that is not even darkness. This is alpha, the most uniform shape there is, the floor of the complexity, the beginning. And now it begins to move. The points stream outward, all of them, spreading away from that impossible smoothness. And here is the thing you must watch for, the thing that overturns everything you expect. You expect the spreading to be a thinning, a dissipation, the way a drop of ink disperses in water until it is nothing but a faint, even stain. You expect the structure to wash out. But that is not what happens. As the points move apart, they do not smear into featureless mist. They gather. Here, a few of them fall toward one another and form a knot. There, a cluster draws itself together, and within that cluster, smaller clusters, and within those, smaller still. Filaments stretch between the knots. Voids open in the spaces between. What began as a smooth, even ball is becoming, before your eyes, a structured thing, a cosmos of clumps and groupings and hierarchies, more intricate with every moment, more full of distinct and separate parts. The complexity is climbing. You are watching order being born, not destroyed. You are watching the arrow of time being drawn, and it is pointing, unmistakably, toward more structure, not less. Come back to your breath, to the quiet of the room, because what you have just watched is not a metaphor, and it is not a special case dreamed up to make a point. It is what Newton's own equations do when you set a gravitating universe loose from its most uniform state. The order increases, the structure grows, and that simple fact that gravitating universes become more organized as they age rather than less runs headlong into the single most trusted law in all of physics, a law that says the exact opposite, a law that Einstein himself swore could never be overthrown. That collision is where we go next, and it is the moment where Barbour stops being a gentle eccentric with cardboard triangles and becomes something far more dangerous to the established order. A man who says the second law of thermodynamics has been misunderstood. Part 8. The Arrow, Reversed. Now we arrive at the heart of the danger, and I want to slow down, because this is the idea that could get a physicist in real trouble, and it deserves to be laid out with care. For about 170 years, physics has had one, and only one, accepted explanation for why time has a direction. Why does the past differ from the future? Why does a cup fall off a table and shatter, but never gather itself back together and leap up onto the table? Why do we remember yesterday and not tomorrow? Why does milk stir into coffee and never unstir? The answer, the standard answer, the answer in every textbook, is entropy. Entropy is, roughly, a measure of disorder, of how many ways the pieces of a system could be rearranged without your noticing any difference. And the second law of thermodynamics says that entropy in an isolated system always increases. Disorder always grows. Order always decays. The cup shatters because a shattered cup is more disordered than a whole one, and disorder is where everything is always heading. This one-way slide from order into disorder, the physicists tell us, is the arrow of time. It is the deepest reason the future feels different from the past. And the story does not stop with cups and coffee. Extended to the whole cosmos, the second law delivers a bleak prophecy. If disorder always increases, then the universe as a whole must be running down, like a clock whose spring is unwinding. The stars will burn out, the structures will crumble, everything will spread into a thin, cold, featureless sameness, a final state of maximum disorder that physicists have long called the heat death of the universe. A cosmos that ends not in fire, but in a lukewarm, uniform, eternal nothing. Every difference erased, every structure dissolved, nothing left to happen anywhere ever again. This is, for many people, the single most depressing idea in all of science, and it follows, apparently inescapably, from the second law. The second law is not a minor rule. It is regarded as perhaps the most secure statement in all of physics. Two great physicists said things about it that Barbour likes to quote, and I want you to hear both, because they show just how enormous the thing is that Barbour is daring to question. The astronomer Arthur Eddington wrote that the law that entropy always increases holds, he thought, the supreme position among the laws of nature. If someone points out to you, Eddington said, that your pet theory of the universe is in disagreement with the second law of thermodynamics, then he could offer that theory no hope. There was nothing for it, he said, but to collapse in the deepest humiliation. And Albert Einstein himself said that thermodynamics was the one physical theory of universal content that he was convinced would never be overthrown, within the framework of applicability of its basic concepts. Read that last phrase again, because Barbour builds everything on it, within the framework of applicability of its basic concepts. Einstein, being Einstein, was careful. He did not say the second law is true always and everywhere. He said it will never be overthrown within the framework where its basic concepts apply. And then, crucially, he never spelt out what that framework of applicability actually was. He left the boundary unmarked. He told us the law reigns supreme inside its proper domain, and he did not tell us where that domain ends. Barbour's claim, in its boldest form, is that people simply forgot that there was a boundary at all. They took a law that was worked out under very specific conditions and quietly assumed it must apply to everything, everywhere, including the universe as a whole. And when Barbour looked inside Newton's gravity, at those universes we have been building, he found order increasing, not decreasing. He found the complexity climbing. He found structure growing richer over time, clusters forming, hierarchies deepening, the exact opposite of the slide into featureless disorder. In his own words, the mainstream picture says the universe goes from being ordered to being uniform and uninteresting, and what he finds coming out of Newton is exactly the opposite behavior. Not a running down, but a building up. Not decay, but creation. Not a march toward heat death, but a march away from a bland uniform beginning, toward ever more intricate structure. To see why Barbour's reversal is so provocative, it helps to understand where the ordinary arrow really comes from, because the standard story is cleverer than a slogan about disorder. The physicist Ludwig Boltzmann, in the 1870s, gave the deepest account. He said that a disordered state is not disordered by decree, but simply because there are so many more ways to be disordered than to be ordered. Think of shuffling a deck of cards. There is exactly one arrangement that counts as perfectly sorted, and there are astronomically many arrangements that count as shuffled. So a shuffle almost never lands on sorted, not because of any force forbidding it, but simply because sorted arrangements are so rare among all the possibilities. Entropy, in Boltzmann's hands, is a measure of how many microscopic arrangements look the same from the outside, and it increases because the universe, blundering blindly among possibilities, is overwhelmingly likely to stumble into the common, high-count, disordered states rather than the rare, low-count, ordered ones. It is not a law of decay, it is a law of counting. But here is the crack that has bothered thoughtful physicists ever since. And it is the crack Barbour drives his wedge into. Boltzmann's counting argument is perfectly symmetric in time. It says disorder is overwhelmingly likely in the future, but by exactly the same reasoning, it says disorder should have been overwhelmingly likely in the past too. The mathematics has no preferred direction. So why was the past so ordered? Why did the universe begin in an extraordinarily low entropy, highly ordered state, when the counting says such states are almost impossibly rare? Physicists call this the past hypothesis, and they mostly just assume it, as a brute fact about the beginning, an initial condition of staggering and unexplained orderliness, that the whole arrow of time then flows away from. Barbour finds this deeply unsatisfying, and his framework offers something the standard story cannot. It does not need to assume a miraculously ordered past. In his gravitating universes, the low complexity, uniform state is not an unexplained miracle. It is the natural flaw of the complexity, the one shape the number bottoms out at, and structure grows away from it automatically, in both directions, without anyone having to pin an improbable beginning on by hand. Where the orthodox account shrugs and says the ordered past just happened to be that way, Barbour says the uniform beginning is where the complexity is always lowest, and everything follows from that. I want to be very careful here, because it would be easy to overstate this, and Barbour himself does not overstate it, and neither will we. He is not saying that entropy is a lie, or that the second law is wrong, or that your coffee cup will start reassembling itself. Within an ordinary system, entropy really does increase, and Barbour cheerfully agrees that it does. What he is saying is subtler and, I think, more interesting. He is saying that the second law, as we normally state it, describes a particular kind of situation, and that the universe as a whole is not that kind of situation. He is saying that the arrow of time, the direction we call forward, might not come from disorder increasing at all. It might come from complexity increasing, from order growing, from the universe becoming, over its history, a more structured and more varied place, exactly as Leibniz dreamed it should. Let me ask you to feel, for a moment, what it would mean if he were right. Not the mathematics of it, but the weight. You have almost certainly absorbed, somewhere along the way, the idea that everything falls apart in the end. That order is a temporary accident, a local eddy in a river, running relentlessly toward disorder, and that the deepest truth of the universe is decay, that the structures we love, the stars, the living things, the patterns, are all borrowed against an inevitable slide into cold uniform nothing. It is a quiet grief that sits underneath a lot of modern thinking, this sense that the cosmos is fundamentally winding down, and that all our building is only a slower kind of falling. And Barbour, from his farmhouse, with his cardboard and his complexity, is gently suggesting that it might be exactly backward, that the natural tendency of a universe under gravity is not to fall apart, but to come together, not to smear into sameness, but to gather into structure, that the growth of order, the increase of complexity, the building of things ever more intricate and varied, might be the truest thing the universe does, the very meaning of the direction we call forward, and that you, an intricate structure that gravity and time somehow assembled out of a smooth beginning, are not a doomed exception to the universe's decay. You are an example of what the universe, at its deepest, is actually for. I do not offer that to you as proven fact, and Barbour would not either, but I offer it as a real possibility, held out with serious mathematics, by a serious man, and that alone is enough to make you look at the night sky a little differently. Still, a careful listener will have a hard, sharp question at this point, and it is the right question to ask. If the second law is so secure, so triumphant, so endlessly confirmed in laboratories, how can it possibly be pointing the wrong way about the universe? What exactly is the difference between the systems where entropy rises and the universe where, Barbour says, order rises instead? The answer is a single, humble, almost comical object, an object that turns out to be hiding inside every experiment on thermodynamics ever performed. The answer is a box, and once you see the box, you cannot unsee it. Part 9. The box that was always there. The most important object in the history of thermodynamics is not a great machine or a famous instrument. It is a box, a container, a vessel with walls. And Barbour's claim is that this humble box has been quietly present at the birth of every idea we have about entropy and disorder, so present, so taken for granted, that almost no one ever thought to ask what would happen if it were taken away. Let us trace the box through history, the way Barbour does, because once you see it appear again and again, the whole argument snaps into focus. The story of thermodynamics begins in the year 1824, with a young French engineer named Sadi Carnot, who wrote a small, brilliant book about the motive power of fire. Carnot was not asking cosmic questions, he was asking a practical one. How efficient can a steam engine possibly be? How much useful work can you squeeze out of the heat of a fire? And to analyze this, Carnot pictured steam trapped inside a cylinder, pushing a piston, confined by walls. The steam had to be contained. A steam engine whose steam simply escaped into the open air would do no work at all. The whole analysis, from its very first breath, assumed a box. 25 or so years later, Carnot's practical questions blossomed into the first two laws of thermodynamics, and into the precise definition of entropy given by the German physicist Rudolf Clausius. And when you look closely at Clausius's definition, Barbour points out, it is all about a system in a box, a quantity of gas, confined in a container whose volume can be slowly changed, with careful attention to how heat flows in and out through the walls. The box is not incidental, it is absolutely central. The definition does not even make sense without it, because entropy, as Clausius framed it, is about how a confined system responds as you adjust its container. Then came the great atomic explanation of heat, the achievement of Clausius again, and Maxwell, and Boltzmann, and Gibbs, the physicists who showed that all this talk of heat and entropy could be understood in terms of countless tiny molecules in motion. And what did they picture? Molecules in a box. Tiny particles bouncing around inside a container, colliding with one another, ricocheting off the walls, elastically, endlessly. Every calculation, every derivation of the second law from the behavior of atoms assumed those particles were confined, bouncing off walls, trapped in a bounded region of space. The box is there, again, at the foundation of the atomic theory of heat, as essential and as invisible as ever. And now Barbour asks his devastating question, the one he says almost no one has seriously asked. What happens if the box is not there? He is willing to stick his neck out on this. He does not think anyone has genuinely worked out what thermodynamics becomes when you remove the container, when there are no walls, when the system is not confined to any bounded region at all. And this matters enormously because of one simple observation. The universe is not in a box. There are no walls at the edge of everything. There is no container holding the cosmos in a bounded region, no vessel with sides for the galaxies to bounce off. Whatever the universe is, it is not a gas in a cylinder. And if all our understanding of entropy and disorder was built, from Carnot onward, on the assumption of a box, then applying that understanding to the boxless universe is not a safe extrapolation. It is a leap across exactly the boundary Einstein warned about and never marked. It is using a law outside the framework of applicability of its basic concepts. Why does the box matter so much? Barbour gives a reason that is precise and, once you grasp it, genuinely illuminating. The key, he says, is that entropy depends on a length scale, on a fixed size against which things can be measured, and the box is what provides that size. The walls of the container give you a definite volume, a definite length, and against that fixed length, you can meaningfully talk about probabilities, about how likely a given arrangement of molecules is. But the complexity, Barbour's measure of order, is scale invariant. It needs no box, no walls, no fixed length, because it depends only on shape, only on proportions. This is the profound difference between the two arrows. Entropy is a concept that only works when you have smuggled in a ruler, in the form of a container. Complexity works without any ruler at all. And so, in a universe with no box and no ruler, entropy loses its footing, while complexity sails on, perfectly well defined. Barbour makes this concrete with a lovely little parable about a deck of cards, and it is worth walking through slowly, because it shows exactly where the standard reasoning breaks. Suppose you have an ordinary deck of 52 cards. What is the chance of drawing the King of Hearts? 1 in 52. Simple, clear, meaningful, because there is a definite, finite number of possibilities. Now suppose, instead, that you had a deck with infinitely many cards in it. What is the chance of drawing any one particular card? You put your hand into an endless bag and pull out a single card. The chance that it is any specific card you name in advance is 1 divided by infinity, which is 0. Every individual card has probability 0. The whole notion of probability, of one outcome being more or less likely than another, quietly collapses when the number of possibilities becomes unbounded. You simply cannot do the usual reasoning anymore. And this is not Barbour's invention. He points out that the great American physicist Willard Gibbs, whom Einstein called the greatest mind in American history, saw this very problem more than a century ago. In his foundational book on statistical mechanics, Gibbs added a careful caveat. He noted that there are circumstances in which the coefficient of probability, the thing you need to make the whole statistical machinery run, simply vanishes, and the law of distribution, as he put it, becomes illusory. That is exactly the deck with infinitely many cards. That is exactly a system that can spread without bound, unconfined, boxless. Gibbs himself, the master of the field, flagged that his own methods stop working when the system is not contained, and Barbour's argument is that the universe as a whole is precisely such a system. It is the deck with infinitely many cards. It is the gas with no walls. It is the situation Gibbs warned about, where the tidy probabilities become illusory, and with them the neat statistical argument that entropy must always increase. There is a piece of this that I find especially satisfying, because it shows Barbour is not trying to abolish the familiar arrow, only to put it in its proper place. He is entirely happy to agree that within the great boxless universe, smaller regions can behave like boxes. A cluster of matter gathers under gravity, holds together for an age, and while it holds together it is, for all practical purposes, a confined system with an effective boundary, and such subsystems do exactly what the second law predicts. Physicists have a name for what they do. They virialize, which is a technical way of saying they settle into the kind of statistical equilibrium characteristic of a confined gas, sharing energy around, wandering toward their most probable arrangements, rising in entropy in the ordinary way. Stars, and the gas clouds that form them, and the clusters that hold them, all pass through this. So the familiar arrow of increasing disorder is perfectly real for these local, temporary, box-like structures. In a sense, Barbour says, his framework can even derive the second law as a thing that emerges for subsystems rather than assuming it as a law of the whole. The running down we see around us, the stars burning through their fuel, the structures slowly dissipating, is the entropy arrow doing its genuine work inside the little boxes the universe throws up. What Barbour denies is only that this local running down is the master arrow, the one that sets the direction of time for the cosmos entire. That master arrow, he says, runs the other way, carried by the growth of complexity in the boxless whole, even as countless little boxes within it quietly wind down. So the two arrows are not really in contradiction at all, once you see the box. Inside a box, entropy rises, disorder grows, and the familiar arrow points the familiar way. And Barbour cheerfully grants that within the universe, all sorts of subsystems do form little boxes of their own. Clusters gather, hold together for a while, and behave for all the world like ordinary confined thermodynamic systems, rising in entropy, running down, dissipating. He even says that in a sense his framework can derive the second law, as something that emerges for confined subsystems, rather than as a fundamental law of everything. But the universe as a whole, the boxless totality, is not governed by that arrow. Its arrow, the deep one, the one that sets the very direction of time, comes from the complexity, from the growth of order, from the climb away from that smooth uniform beginning toward ever richer structure. The heat death was always a prophecy about a box, and the universe, it turns out, has no walls. I find this one of the most quietly thrilling turns in the whole story, because of how ordinary the culprit is. We were told the universe is doomed to dissolve into featureless heat, and the reasoning felt airtight, ancient, unshakable. And Barbour's response is not to attack the mathematics or deny the experiments. It is to point gently at a box that was sitting in the corner of every derivation the whole time, holding the walls up, providing the ruler, and to ask what becomes of the argument when the box is removed. The vanishing ruler we met when we talked about size has returned, wearing a different costume. Back then it was Poincaré's undetectable expansion, the fact that absolute size is meaningless without an external standard. Now it is the box, which turns out to be nothing more than a ruler smuggled back into physics through the walls of a container. And the universe, having no ruler and no box, is free to run its arrow of time the other way. Which raises a question that Barbour, restless and unwilling to leave anything alone, could not help but ask next. If the complexity is what really increases, if it is the true measure of the universe's progress, then perhaps the complexity is not just correlated with time. Perhaps the complexity is time. And chasing that thought takes us into the strangest territory yet, where even the quantum world begins to dissolve into shapes. Part 10. A clock made of shape. Once you have decided that time is not a fundamental flowing thing, you are left with an obvious and pressing problem. You still have to explain why we experience an order, a sequence, a definite before and after. Barbour's toy universes are collections of shapes, of nows, but a collection is just a heap. What lines the shapes up into a history? What makes one triangle come before another, rather than the shapes simply sitting there in a formless jumble? Barbour's answer is elegant, and it uses the very quantity we have spent this exploration building. The thing that orders the nows, he proposes, is the complexity itself. Remember that in these gravitating universes, the complexity tends to increase, steadily, almost like clockwork, once the system has moved away from its uniform beginning. So you can use the complexity as a label. You can take all the frozen shapes and lay them in the order of their complexity, from the smoothest and simplest to the most clustered and structured. And that ordering, Barbour suggests, is what we experience as the passage of time. The direction of increasing complexity is the direction we call forward. Time is not a river, the shapes float down. Time is just the shapes, arranged in order of how much structure they contain. The clock is not ticking somewhere behind the universe. The clock is the growing intricacy of the universe itself. This is why Barbour can say, in that compressed and startling phrase, that time is just the shape of the universe. When he first said it, early in this exploration, It might have sounded like poetry, a pretty way of speaking. Now you can see that he means it with full mathematical seriousness. There is a number that measures the shape, the complexity, and the direction in which that number grows is the direction of time, not a metaphor, a definition. The shape of the universe, and the way that shape becomes more intricate, is not merely correlated with time, it is what time is. And here Barbour's idea reaches out and touches the single hardest unsolved problem in all of theoretical physics, a problem so notorious it has its own name. Physicists call it the problem of time, and it lives at the border between quantum mechanics and gravity. For 60 years, the greatest minds in physics have tried to combine Einstein's theory of gravity with quantum mechanics to build a quantum theory of the whole universe, and they keep running into the same wall. Back in 1967, the physicist Bryce DeWitt wrote down an equation meant to describe the quantum state of the entire cosmos, an equation that combined the two great theories, and when he looked at what it said, he found something bewildering. The equation described a universe that does not change. The quantum state of the whole universe, according to the mathematics, is frozen, static, timeless. Nothing evolves. There is no ticking T, no flowing time, anywhere in the fundamental equation of quantum gravity. The universe, at its deepest quantum level, appears to just be, without any time at all. For most physicists, this was a disaster, a paradox to be explained away. How can the fundamental equation say nothing ever changes, when we plainly see change everywhere? They tied themselves in knots, trying to recover a hidden time from within the frozen equation, some internal clock buried in the mathematics. But look at it through Barbour's eyes, and the disaster turns into confirmation. Of course, the fundamental equation is timeless. Time was never fundamental. The frozen, static, timeless quantum universe is not a paradox. It is exactly what you would expect if Barbour has been right all along, if reality is a timeless collection of shapes and the flow is something we add. And Barbour's specific proposal is to take his complexity, that steadily growing measure of structure, and use it as the internal clock, the thing that plays the role time plays in ordinary physics. Because there is exactly one shape of minimum complexity, that unique smooth beginning called alpha, the whole construction has a clean, well-defined starting point. The timeless equation, read Barbour's way, describes not a dead frozen universe, but a landscape of all possible shapes, ordered by their complexity, which is to say, ordered by what we call time. He goes further still, into territory he admits is speculative, and it concerns the deepest mystery of quantum mechanics itself. There is a mathematical object in Barbour's shape spaces called the natural measure, a way of assigning, to any region of possible shapes, a definite number, a probability. And this natural measure, his collaborators noticed, behaves uncannily like the probability rule at the very core of quantum mechanics, the rule that tells you how likely you are to find a particle here rather than there. But here is the strange part. The natural measure is just sitting there, a property of the space of shapes, requiring no wave function, no quantum state, and crucially, no Planck's constant, that tiny fundamental number that is supposed to define the scale of all quantum effects. Barbour and his collaborator, Tim Kozlowski, found themselves asking a heretical question. What if there is no quantum mechanics underneath, in the usual sense at all? What if what we call quantum probability is really just the natural distribution of shapes in shape space, and Planck's constant, that supposedly fundamental constant of nature, is not fundamental at all, but something that emerges from the geometry of shapes? It is a staggering thought. It would mean that quantum mechanics, the most successful and most mysterious theory in the history of science, might itself be a shadow cast by the timeless geometry of shapes. There is an objection you may be forming right now, and it is the right one, so let me meet it head on, because Barbour has an answer that reaches back to another of the 20th century's giants. The objection is this: Einstein's relativity, we are always told, forbids exactly the kind of universal now that Barbour seems to need. There is no cosmic instant, no single slice of the whole universe that everyone would agree is happening at the same time, because observers moving differently disagree about what counts as simultaneous. If reality is a stack of nows, complete configurations of the entire universe frozen at an instant, then relativity seems to say there is no well-defined way to take such a snapshot at all. How can Barbour speak of the shape of the whole universe at a moment, when relativity says the moment itself is not universal? Barbour's reply leans on a paper written in 1958 by Paul Dirac, one of the founders of quantum mechanics and one of the most careful thinkers who ever lived. Dirac was wrestling with how to combine gravity and the quantum, and he came to a striking conclusion. If you want to build a quantum theory of gravity, Dirac argued, you will have to restore a notion of simultaneity, a preferred way of slicing space-time into moments, the very thing Einstein had declared meaningless. Einstein had said you could slice space-time any way you liked, like a loaf of bread cut at any angle, with no preferred direction. Dirac said that this freedom, so natural in relativity, is poison for quantum mechanics, because it introduces redundant, unphysical degrees of freedom, extra descriptive baggage that has nothing to do with what is really happening. Better, Dirac suggested, to find the one right way to slice the loaf. This made an enormous impression on the young Barbour, and he has argued ever since that Dirac was essentially right, that there is a preferred slicing, a real cosmic now, hiding inside general relativity when you read it correctly. And here is the part that lifts this out of pure philosophy and touches something we can actually observe. Barbour points out that the universe itself seems to provide such a preferred standard of rest. Filling all of space is the faint afterglow of the early cosmos, the cosmic microwave background. And against that glow, you can define a state of true rest, a frame in which the ancient light looks the same in every direction. Move relative to it, and the glow shifts, brighter ahead and dimmer behind, and you can tell you are moving. So the universe does, to very high accuracy, single out a notion of rest, and with it a natural cosmic slicing, a way of saying what counts as now for the whole of everything. Special relativity, Barbour would remind us, was always meant to hold only locally, in small, free-falling patches, not to govern the whole cosmos. General relativity replaced it, and read Dirac's way, general relativity permits the very cosmic now that Barbour's stack of shapes requires. The objection dissolves, and the shapes are allowed to be shapes of the whole universe after all. To see why Barbour would even dare to think this, you have to understand where all our evidence for quantum mechanics actually comes from. And this is where he tells a story about a single, exquisite experiment. Everything we know about the quantum world, he points out, comes to us in the form of marks, patterns, structures we see with our ordinary eyes, spots on a photographic plate, tracks in a detector, fringes on a screen. We never see the wave function directly. We see the marks it seems to leave, and from those marks we infer the whole invisible quantum machinery. And the most famous of all these patterns is the interference of the double-slit experiment, which the physicist Richard Feynman called the central mystery of quantum mechanics, the one phenomenon that contains the whole strangeness of the quantum world. Come with me, then, into a laboratory in the year 1909. The room is dark, deliberately, carefully dark. A young experimenter named Geoffrey Taylor is preparing something delicate. He wants to send light through a narrow apparatus, but not ordinary light, not a bright beam. He has dimmed it and dimmed it and dimmed it again, until what trickles through is fainter than you can easily imagine. As faint, by later reckoning, as the light of a single candle seen from a mile away. At that faintness, the light is no longer a stream. It is a scarcity. Individual quanta of light, one at a time, crossing the darkness alone, so rare that only one is ever in the apparatus at once, with long stretches of nothing between them. There is nothing for a single lonely photon to interfere with. It has no companions, and so Taylor sets a photographic plate to catch them. And he waits. He waits for months. The exposure runs and runs, one solitary particle of light at a time, drifting through, striking the plate, leaving a single tiny mark, and then another, over weeks, over months, the marks accumulating in the patient dark. And when at last the plate is developed, and Taylor looks at what the lonely photons have written, one by one, with no companions to interfere with, the fringes are there, the bands of light and dark, the interference pattern, built up out of individual particles that arrived alone, each one somehow landing in accordance with a pattern that seems to require the whole. It should not be there, and it is. Come back, slowly, to the quiet. That experiment is one of the strangest things in all of physics, and it has haunted the field for over a century. But Barbour looks at it and asks a question almost no one else asks. He notices how extraordinarily special the setup is. The precise slits, the exact geometry, the particular arrangement of source and plate, all of it engineered with enormous care. And he wonders whether that incredibly special arrangement might not be passively revealing a pre-existing quantum wave, but might instead be forcing a pattern into being, a correlation that the geometry itself demands. Perhaps, he suggests, the fringes are not a message from an invisible wave. Perhaps they are a shape that the special setup could not help but produce. It is a wild thought, and Barbour knows it. He says people just shake their heads when he says it. But it flows directly from his lifelong conviction that shapes and their built-in correlations are more fundamental than the machinery we usually invoke to explain them. And it leads him to a question about all our instruments, and about ourselves, that is stranger and more vertiginous than anything we have met yet. Part 11. Did we make the pattern? There is a thought that has troubled the wiser physicists for a long time, quietly, at the edges, and Barbour walks straight into the middle of it. The thought is this: we build enormous, exquisite, painstakingly special instruments to probe the universe, and we assume that these instruments simply reveal what is already there, that they are windows, passive and clear, through which we glimpse a reality that would be exactly the same whether or not we were looking. But what if that assumption is not quite right? What if the instruments, by their very specialness, by the extraordinary precision of their design, play some role in shaping what they find? Barbour raises this with real seriousness, and he is careful to flag it as among his most speculative ideas, some of it, he admits, only days old at the time he spoke. He points to those instruments we imagined at the very beginning, the ones we assumed were the natural home of frontier physics, the great radio telescopes, the observatories perched at 5,000 meters in the thin, cold, bone-dry air of the Atacama Desert in northern Chile, the electron microscopes that let us see the almost unseeable. Every one of them is a marvel of specialness, a configuration of matter, arranged with a precision found nowhere in raw nature. And Barbour asks, softly, whether it is possible that these marvelous instruments, to some degree, participate in creating what is observed, rather than merely discovering it, whether the footprint we find on the shore of the unknown might, in part, be one we ourselves have pressed into the sand. That image is not mine, and it is not quite Barbour's either. It comes from the astronomer Arthur Eddington, the same Eddington who called the second law supreme, and Barbour quotes it because it captures the vertigo exactly. "We have found," Eddington wrote, "a strange footprint on the shores of the unknown. We have devised profound theories, one after another, to account for its origin, and at last we have succeeded in reconstructing the creature that made the footprint, and lo, it is our own." It is one of the most unsettling sentences in the history of science. We set out to discover what made the mysterious mark, We followed the clues with all our ingenuity, and at the end of the trail, we found ourselves. The footprint was ours all along. Now, I want to be careful, because this is the point where a channel less committed to honesty might tip over into something mystical and irresponsible. Barbour is not saying that reality is whatever you wish it to be, or that the mind conjures the world out of nothing, or any of the comforting fantasies that get draped over quantum physics in the wrong hands. His point is narrower, stranger, and more disciplined than that. He has spent his life showing that geometry is full of correlations that are simply built in, relationships among points that hold necessarily, without any force reaching between them, without any signal passing. He draws a careful comparison to one of the most famous results in quantum physics, the correlations between entangled particles that the physicist John Bell analyzed. Correlations so tight that many people find them spooky, and yet through which, provably, no information can ever be sent. Two entangled particles, measured far apart, show results that are perfectly correlated, and yet neither measurement can be used to send a message to the other. The correlation is real and instantaneous and carries nothing. Barbour suspects that this famous quantum spookiness might be, at bottom, nothing more than the ordinary correlations of geometry, the built-in relationships among things arranged in space, which are also real and instantaneous, and carry no information. The mystery of entanglement, he wonders, might just be the mystery of shape. If that is so, then the special setups we build, the double slits and the telescopes and the microscopes, are ways of arranging matter into very particular geometric configurations, and the patterns they produce might be, in part, the correlations that those configurations necessarily contain. We arrange the world into an exquisite shape, and the shape has consequences built into it, and we read those consequences as a discovery about nature, when they are partly a consequence of the arranging. The observer is not standing outside the universe, peering in through a clean window. The observer is inside, part of the geometry, and the act of arranging an instrument is the act of setting up a shape whose correlations then appear as data. The line we draw between the watcher and the watched, between the measuring device and the measured world, may be one more thing that is not truly out there, one more convenient fiction the mind supplies, like the flow of time and the size of things. Underneath all of this lies a question Barbour cannot stop returning to, the most basic question there is. What is the world actually made of? What is the absolute minimum you would need, the sparest possible set of ingredients, to build everything we see and experience? And his answer is startling in its economy. He thinks you might need nothing more than points in space, all of the same kind, perhaps all of the same mass, and the distances between them. Not little billiard balls with surfaces and colours and textures, just mathematical points, and the web of separations among them. From that, he suspects, in principle, all the structure of the world could be built. The proportion of the distance between your eyes, to the distance from your eyes, to the tip of your nose, and every other structural fact about everything, could in principle be encoded in nothing but points and the relations between them. He calls this the structure of the world, and he thinks it might be all there is, at the level of physics. But then he stops, with real humility, at the one thing this spare picture cannot deliver. It cannot explain why there is any experience of it at all. It can give you the geometry of a face, but not the seeing of the face. It can give you the arrangement of air and eardrum, but not the hearing of a voice. The fact that you do not merely register geometry, but actually experience colour and sound and warmth. The fact that there is something it is like to be you, sitting here, listening. Barbour sets carefully to one side. He calls it a gift. The underlying reality may be only points and distances, only silent structure, and then, laid over it somehow, is the gift of consciousness, the seeing and hearing and feeling that the bare geometry does not contain and does not explain. He does not pretend to solve this. He simply marks it, honestly, as the place where his points and distances picture reaches its edge. There is an old lineage to this obsession with shape, and Barbour delights in it. He points back to the ancient atomists, and above all to the Roman poet Lucretius, who 2,000 years ago wrote a long poem on the nature of things, trying to explain all the endless forms of the world out of tiny, indivisible seeds. What the ancient thinkers were really chasing, Barbour says, was an explanation of shapes, why children resemble their parents, why each kind of tree keeps its form, why the world is full of distinct and repeating patterns rather than formless mush. And he is charmed, almost childishly charmed, by a coincidence buried in language itself. The Greek root of our word idea, he points out, is a word for shape, or pattern, or form. The very word we use for a thought traces back to the word for a visible shape. He notices that the word pattern traces back, through its roots, to father, and the word matter traces back to mother, so that the world, the child, is born from the marriage of pattern and matter, form and substance. He offers these not as arguments, he is far too careful for that, but as small delights, hints that the human mind has always sensed, in its oldest words, that to understand the world is to understand its shapes. I find this the most disorienting stretch of Barbour's thought, and I want to hold it at the right distance for you. It is not established physics. It is a lifelong relationalist, at the far edge of his own ideas, wondering aloud whether the deepest mysteries of the quantum world might dissolve, like time and size before them, into facts about shape and relationship. He may be wrong about this. He would say so himself. But notice the shape of the suspicion, because it rhymes with everything that came before. Again and again, Barbour takes something we assumed was fundamental and absolute, standing outside and above the relationships among things, and he folds it back in. Time, we thought, flowed above the universe, and he folded it into the changing shapes. Size, we thought, was measured against an external ruler, and he folded it into the internal proportions. And now the observer, whom we thought stood outside, looking in through clean instruments at an independent world, he folds back into the geometry too, part of the shape, part of the pattern, no longer a spectator, but a participant in the very configurations being measured. It is the same move, made over and over, on ever deeper targets. Remove the imagined external absolute, keep only the relationships, and find, each time, that the relationships were enough, that they were, in fact, all there ever was. And this relentless folding in leads Barbour, at the very end, back to the most intimate absolute of all, the one closest to home, the one you are using at this very moment to follow these words. It leads him back to your own mind, and to your memory, and to the flow of time you feel most certain of, the flow inside your own experience. Because if time does not exist out there in the universe, then the last place it seems to hide is in here, in the undeniable sense that you have a past, that you remember, that you are moving through your own life. And Barbour has something to say, gentle and strange, about that too. Part 12. Nows, Time Capsules, and the Question That Remains. We have come a long way from the farmhouse and the cardboard triangle, so let me gather the threads, slowly, the way you might gather a blanket around yourself at the end of a long day. Barbour's universe, in the end, is a collection of nows. Complete, frozen configurations of everything there is, each one whole, each one entire, none of them flowing into any other. There is no river of time carrying them along. There is only the enormous stillness of all the possible shapes, all the possible arrangements of the universe, existing not one after another, but simply existing. And what we call the passage of time, the sense that we move from one moment to the next, is the way these still shapes are ordered by their complexity, from the smooth and simple toward the clustered and intricate, and the way a mind, embedded in them, reads that ordering as a story of before and after. But this leaves the most personal question of all. and it is the one that should be nagging at you by now. If there is no flow, if reality is just a heap of frozen nows, then why do I feel time so vividly? Why do I have a past? Why am I so utterly certain that I have moved through the day to arrive at this moment, that things have happened to me, in order that I remember? Surely my own experience of time flowing is the one thing that cannot be an illusion, because it is the most direct thing I know. Barbour's answer is perhaps the strangest and most beautiful idea in his whole framework, and he has a name for it. He speaks of special configurations he calls time capsules. A time capsule is a particular kind of now, a frozen shape that happens to be arranged in a very special way. It is arranged so that it contains, within itself, all at once, the appearance of a consistent history. Think of a geological record, the layers of rock laid down in a cliff face. That cliff, right now, in a single present moment, contains what looks like an ordered story of the past, epoch upon epoch, stacked in sequence. But the whole record is simply there, all at once, in the present arrangement of the rock. You do not need the past to still exist somewhere for the record of it to be present now. The record is a feature of the current shape. And Barbour says, quietly, that your brain is a time capsule. Your brain, in this single frozen instant, is arranged in an extraordinarily special configuration, one that contains, all at once, the memories, the impressions, the sense of a life lived up to this moment. The feeling that you have moved through time is not evidence that you have moved through time. It is a feature of the shape your brain is in, right now, in this time. Every memory you have of a moment ago is present, complete, in the current configuration, the way the whole geological story is present in the current rock. You are not a thing moving through a sequence of moments. You are a shape that contains, within itself, the vivid impression of having moved. The river of time is inside the frozen frame, painted into it, sealed within a single still picture that somehow holds the feeling of flow. Rest here for a moment, at the very end, inside a single now. This one, the one you are in, it is complete. Everything is here, all at once. The particles of your body in their exact arrangement, the particles of the room, of the air, of the light, the pattern in your brain that holds the memory of the sentence before this one, and the one before that, and the whole long path that seems to have brought you here. All of it, present, together, in this single, frozen shape. And notice, if you can, that nothing is actually moving. There is no next moment arriving. There is no previous moment departing. There is only this complete arrangement, entire in itself, holding within it the full and convincing sensation of a flow that is not, in this deepest picture, happening at all. The feeling of time passing is here, inside the now, real as a feeling, woven into the shape. But the passing itself, the river, the current carrying you forward, is nowhere to be found in the arrangement, because there is nothing outside the arrangement for it to be. You are not being carried anywhere. You simply are, this shape, containing this feeling of having become. And the strangeness of that, the soft, impossible stillness underneath the sense of motion, is perhaps the closest you will ever come to seeing time the way Barbour sees it. Come gently back, and let me return, as I promised, to that old phrase from the very beginning. Time, the line goes, is what stops everything from happening at once. It always sounded so wise, so neatly true, but now you can see how completely Barbour turns it over. In his picture, nothing stops everything from happening at once. Everything does happen at once, in the only sense that matters, because all the nows simply are, together, in the timeless stillness of all possible shapes. Nothing holds them apart into a cue. The cue is what the mind makes when it finds itself inside one of those shapes, reading the record the shape contains, feeling the flow the shape holds. The universe is not protecting us from everything happening at once. Everything happening at once, all the shapes existing together, may be exactly what the universe is. And the sequence, the spacing, the one thing after another, is our doing, not the world's. This is why Barbour named his book after Janus, the ancient two-faced god, who looks in both directions at once, toward what we call the past and what we call the future, from a single, still point between them. Because if order grows away from that smooth, uniform beginning, it may grow in both directions, two arrows of time streaming out from one moment of minimum structure, each side calling the other its past. It is a picture of quiet, enormous symmetry, and it dissolves the lonely one-way river we thought we were trapped in into something stranger and more spacious. I have to be honest with you, here at the end, in the way that this channel always tries to be, none of this is proven. Julian Barbour would insist on that himself, and in fact he does, plainly, in his own words. He says he and his collaborators are a long, long way from being able to claim they have a new theory of the universe. Whether the real cosmos truly has a Janus point, whether the complexity truly plays the role of time, whether quantum mechanics really dissolves into probabilities for shapes, whether Planck's constant really emerges rather than stands fundamental, all of it is open, unfinished, uncertain. What Barbour offers is not a finished answer. It is a different question, asked with unusual seriousness and unusual patience, from a farmhouse the mainstream mostly drove past for 50 years. But think about how fitting that is. A man who freed himself from the clock of academic deadlines, who refused to slice his thinking into annual portions, who bought himself the one thing a truly hard question needs, which is time, or rather, which is the freedom to let his mind change shape slowly, without being hurried. He spent that freedom asking whether time is real, and came to suspect it is not, that there is only change, only the shifting shapes of things, only the growth of order out of a smooth beginning. There is a gentleness in where that leaves us. We are not doomed structures in a universe running down toward cold nothing. We are intricate shapes, gathered by gravity and complexity out of a uniform dawn, examples of the very thing the universe, at its deepest, seems most inclined to do, which is to build order, to make variety, to become, in Leibniz's word, more varied than it has to be. And the flow you feel, carrying you now towards sleep, may not be a river at all, but a stillness so complete that it holds, within a single frozen shape, the whole warm feeling of a life in motion. Thank you for spending this long, quiet hour with me, wandering through the idea that time might not exist. If this kind of slow exploration is how you like to drift off, a like or a subscribe would mean a great deal, and it genuinely helps me keep making these. And remember, the next time you feel a moment slipping away into the past, that it may not be going anywhere at all, only sitting, complete and still, among all the other shapes of everything there is. Good night, and may you never look at the passing of time in quite the same way again.